All right. First and foremost, I would like to deeply thank the organizers for the opportunity to talk here. I know there are lots of logistics involved, especially when you come from another continent. But I'm looking forward to. I mean, I'm deeply honored by the initial talk, and I foresee many opportunities, discussions over the week. All right, today's talk is like a revision of the work I've been doing in the last few years in my own quirky and proper way to look at this. I mean, my own way to look at this, idiosyncratic as it is. I understand most of the some other people later on, but I'll try to. So, the outline, it's a bit on mathematics side, so I beg your patience a little bit. I'll be revising some very basic stuff about differential equations in the complex plane and their relation to flat holomorphic connections. I mean, this is basically how I got into the game in the first place, and how the problems that we use to think in physics, they are best solved, in my opinion, of course, but they are best solved by thinking about the analytic structure of the solutions of these differential equations. And this is a 100-year-old problem in mathematics, and it's called the RiemannHillbert problem. It's 21st, I think, of the Hilbert problems for the mathematics in the 20th century. But I think there are great strides that came from it and came from the interaction between CFT and gauge theory of all things in the last few years. And I've been moving to the application, which I think is the most physical part of it, and it's basically talking about quasi-normal modes, and I'll try to explain why this is a natural application to think about these mathematical issues. And if time permits, I will be talking about some other application in applied mathematics that are being focused in the last few years, which I think that they also have a counterpart in physics. They also will help some of the mathematical issues behind the physical problems that you can solve using the technique. And I would like to take the opportunity to thank the various collaborators. I outlined these issues in the last few years, especially Juan Barragan Amado, João Paulo Cavalcante, which I understand the family came from here, so I guess it's a local boy 400 years later. Tiago Anselmo, Fábio Novaes, especially Juan Barragan and João Paulo, which do not have a job yet, so I guess that they will be most happy to be remembered. Salman Nejad, Elisabetta Palante from Groningen, Rodri Nelson, and Derek Crowdy from the Imperial College London. All right, so let me start from the basics. Usually you think about the differential equation, ordinary differential equation, the complex plane, as a scalar equation. It is best for us to consider both solutions of this second order differential equation at the same time. So we arrange the solutions neatly in this phi matrix, which it's called the fundamental matrix of solutions. And if you phrase this differential equation as a second order differential equation at a 2x2 matrix system, this differential equation becomes like the matrix equation that I've just written at the beginning, and this matrix of coefficients, which in general are functions in the complex plane, can be thought of as a flat holomorphic connection. I guess this is pretty standard. The A has the form of a flat SL2C holomorphic connection, and you can think about that in those terms. I mean, not only in terms of the parameters of the gauge field, but also in terms of observables, or what physicists would think about an observable of a gauge field. Well, the important bit for us to understand how the procedure works is to write a differential equation for the first line of the fundamental matrix phi, the equation for y2 and y1. And you can see the differential equation has this genetic structure that's given the second line. And it's a second order Fuchsian differential equation if A has at most single poles, single poles. But you see that the differential equation has not only the poles, well, the associated poles of singular points associated to A itself, but also with the zeros of the 1-2 entry of the matrix A. So this comes about exactly from this term over here and that term over there. Despite being an extra singularity, you can convince yourself very easily that this singularity is what the mathematicians call apparent singularity, because the analytic properties of the function there are mixed solutions. So if you go around the complex plane around the singularity, the solution will come back to itself. And this, this has a trivial monodromy, as you see. And this is an extra structure that you need from the differential equation. So people at first were very puzzled about this. This is a 100-year-old property, but they soon realized that you need those apparent singularities in order to work the definition of the function itself from the analytic structure, from the complex structure. And this is exactly the problem that we set out to solve. It's called the RiemannHillbert problems. How the parameters in this gauge field, A, they affect the analytical behavior of solutions. Sorry. Yeah, it's over here. So, okay. Huh?
Okay. Z is on the complex Riemann sphere, not on a Riemann surface.
Yeah, in this case, it's a Riemann sphere.
Okay.
Yeah, I'm sorry if I gave some other impression, but no, it's on the Riemann sphere. I'm trying to keep it simple. You can do it genetically G G, but this is not what we want. So, okay.
Y1, Y2 are the two solutions of this equation?
Exactly. The two solutions that I'm worried about. W1 and W2 they are sort of auxiliary functions. They are related to the functions Y1 and Y2 by some simple rational behaviors. I mean, they really have the same analytic behavior. So just to sum up, I mean, yes, Z in the Riemann sphere. You can do that in the genus 1. It's a bit more complicated, but there are people from CISA that are wondering about that, and we think that you have some good application for those constructions as well. But this is a different problem. Anyway, the problem that we set out to solve is how the parameters in this gauge field, A, they affect the analytical behavior of the solutions, Y1 and I2. So the first thing I need to tell you now is, the second thing I need to tell you is how the analytic behavior of the solutions is encoded. And this comes from this monodromy properties. So in general, you have, I mean, it's a solution of a Fuchsian equation. You have these singular points, in this case, in the simplest case that you can think about, the singular points are all regular singular points. You don't have any Stokes phenomenon, anything like that, just branch cuts, which I'm not drawing here. And you have in the simplest case, you have 4 of those singular points. I mean, you can have 3, but that's a hypergeometric function that we all know and love. Well, if you have 4 of those, this is also a known function you can put into Mathematica, and I mean, if you want to, your life is very simple. Mathematica will tell you everything about that. I'm talking about a bit more about the structure rather than the actual solutions. So the structure here is that if you go around each of these singular points in the complex plane, then in general you pick up a phase. Well, if you write your preferred method of solving these differential equations in the complex plane, like Frobenius method, you find solutions which are Y1 and Y2, they have a very definite behavior near one of those singular points, and so what happens after you go around the singular points is that you pick up a phase. Well, theta can be actually a generic complex number, but I'm saying phase as a sort of poetic license here. But the important bit is that once you solve the initial equation in a Frobenius method, then the phase that you pick up is diagonal. You don't mix two different solutions. Well, this of course won't happen if you try to go with the solution that you built as a singular point zk through another singular point. So you go through another singular point, like you construct the solution, for instance, from 0, and you go around the singular point at t0. Well, if you do that, then generically you have to change the solution to write the solution that you have at 0 in a basis where the monodromy property of t0 is diagonal. And if you do that, you get a non-trivial matrix. And in the case of 4 singular points, the structure of these monodromy matrices up to choice of basis of solutions is kind of simple. You have the conjugacy class of each one of these monodromy matrices at each singular point. I'm counting infinity as well, since I'm working the sphere. And these are easily readable from the differential equation itself. So you don't have any extra piece of information here. What is less clear from the differential equation are the compositive monodromy matrix. So this one, when you take one particular solution and you go around 2 of the singular points, I'm writing here 0 and t0 for illustration. If you do that, then you have a non-trivial monodromy matrix, which I'm referring as a composition of MT and M0 over there. And this defines to you this composite monodromy parameter. I'm calling it sigma here. This is my own idiosyncratic way of doing that. There are many different choices. And you have conjugate to that the so-called eta parameter, which basically tells you how the monodromy properties between 0 and t0 are related to 1 and infinity. If you work in a basis where m0, m0 is diagonal, then m infinity, m1 is also diagonal, but since diagonal matrix can be related by some conjugation by a diagonal matrix itself, you need an extra eta parameter. These are the so-called Fenchel-Nielsen coordinates for the monodromy matrix well, with 4 singular points. And these tell you is basically what, everything you need to know about these global analytical properties of the functions. There are generalizations for any number of points in the sphere. And for genus 1, things are not so much complicated, but this becomes a real hassle if you work in generic genus G, and people don't even know if you can, well, you can represent the generic monodromy matrix using these coordinates. Another question? Okay.
So, the 4-point function equation is the Hoyne equation. Okay?
Yeah, in this case it's Hoyne, yes.
I thought that the connection matrices for Hoyne equation weren't known. Are you saying that they are known?
You mean they are not?
Known. The connection...
No, I'm sorry, I guess I didn't understand the statement is that the connection properties of Hoyne are not known.
No, yes, the connection... I mean, given the solution around one singular point, how these solutions are connected exactly to the solution around a different point. So I thought that they weren't known, are they?
Well, I mean, I'm stating, and this is the problem that I actually solved, is that, I mean, they are not known, but the monodromy properties, they constrain the connection matrix well enough so that you can solve the scattering problem. And this is the basic one-sentence version of the results I'm trying to present. Okay. It is a problem for a conformal mapping because you actually need to solve for the connection matrices, but well, that you cannot do. But you can solve it. You can constrain it well enough so that you can solve the scattering problem by using monodromy. This is, I guess this is the fair statement. Anyway, I mean, this is the structure of the, just to come back here, this is the structure of this monodromy properties of the differential equation. Now, okay, I guess I jumped ahead a few slides, yes. The important bit now is to understand how you do this translation between the parameters in the equation and these monodromy properties, which, I mean, you gave the spoiler already, I'm going to repeat that. That the monodromy properties, they constrain the connection properties or connection matrix just enough so that you can solve, for instance, the quasi-normal mode problem in black holes, or well, any scattering problem using Fuchsian and confluent limits of Fuchsian differential equations. But this is the spoiler. But in order to do that, I still need to tell you how to translate between the parameters in the equation, so the parameters in the gauge field, if you think about that, and the monodromy properties of the system. Or the monodromy properties can be thought of as invariant gauge field observables that you associate to it. It's just that this gauge field is a two-dimensional gauge field. Anyway, the important bit for us, I mean, this is my own idiosyncratic way to know about this. I understand that probably Alba is going to give you a completely different view of this, is by using this extra or using this residual gauge symmetry that you have in the system. I mean, given the form of the differential equation, you still have some residual gauge symmetry that allows you to, well, explore and find the monodromy parameters. So, sure.
You are like Zikiki. You are the new Zikiki. Yeah. Okay, so okay. I'm a little bit lost, right? You're solving a second-order ordinary differential equations, mm-hmm. and you're making all this complex construction. Mm-hmm. As you said, this is something that you either solve numerically or analytically in this case. So I'm still missing the reason why you're doing all these complex type considerations. Why do you need...
Why do I need to go over the complex plane?
No, why do you need these symmetry?
Right, okay.
All these gates and so on to solve a second-order differential equation?
Because we want to? No, but let me try to be a bit more precise. Look, solving differential equation has different meanings to different people. If you look, I mean, if you ask your student of mathematical methods, second year, third year students in physics, what do they mean by solving a differential equation? Is to write a differential equation in terms of fundamental functions. Well, and I guess everybody here knows that in general you cannot do that for this type of equation. So this is out of the point. So what do you mean by solving then? Well, I mean, then it comes the second bit. The second bit is now somebody that went through mathematical methods will tell you, oh, I can give local expansions of solutions. And this is a way to solve it, at least close to the singular points. And this is known as Frobenius method. Okay? I'm maintaining that, and this is the important bit, this is not what we want in physics. This is in the next year course in quantum mechanics, they will not ask you what is the value of the wave function at r equals 0.5. They will ask you what is the connection between the function that you have, what one singular point, say minus infinity, and another singular point plus infinity. That's called the scattering matrix. Mm-hmm. And this is the problem that I'm setting out to solve here. Is it good enough? Great. And then, I mean, I gave the spoiler already that, okay, you can ask now the following question. Why do you have to worry about monodromy properties? I'm telling you that monodromy properties are well, elegant for sure, but also useful way to think about these connection matrices. How to relate the functions at different points. Anyway, I'm going very fast here, so because I guess I'm out of time already. So this is the residual gauge symmetry that you have in the system. Even though you set the system to be this second order differential equation from the first order matrix system, you still have some residual symmetry. Residual symmetry has to do with the position of this extra apparent singularity that you have in the second order differential equation. Well, you can work out, this has been done 100 years ago by these people, Schlesinger and Garnier, Painlevé himself, and all the other, Lázaro Fuchs, and everybody that followed through this initial insight by so many people, so many names. The initial insights by Liouville. These are called the Schlesinger equations. These they modify the position of this extra apparent singularity so that they keep the monodromy data invariant. And this is the thing I'm telling you. I mean, I'm basically interested in solving for the monodromy data. Well, if you work out this action, so called Schlesinger flow, in terms of the ODE of the differential equation that we actually want to solve, you see, as I already anticipated, that you're going to get an extra singularity at lambda, and this extra singularity at lambda being apparently means that you have some algebraic relation between k, mu, and lambda. K can be thought of as basically as the Hamiltonian of this flow. This flow is Hamiltonian. This is one of the greatest achievements of Schlesinger himself. And this residual gauge symmetry can be thought of as varying the position of this accessory, the apparent singularity, and modifying this lambda, the mu and lambda accordingly so that this extra singularity still is apparent. Well, the Hamiltonian K has a generating function. I mean, this is a classical integrable system, so it means it can be solved by Hamilton-Jacobi or the usual way. And the generating function of this canonical transformation that solves the system is called the tau function. The name tau function gives another a plethora of other interpretations. I'm not going to go into there here, but let me just tell you that the system of this tau function also shows in a lot of quantum systems, like the Ising model and so on. Exactly the same one, by the way. But the way it shows up there is completely different. In our case, or in our strategies, we want to use this tau function to find the monodromy data. And the reason will be in the next slide, why this tau function tells you about the monodromy data. In our case, or in our point of application, just means that you're going to choose initial conditions for this Hamiltonian system so that it passes through the differential equation that you actually want to solve. But you deform the differential equation in a way that keeps the monodromy data invariant. And this is the initial condition that you find here is well posed. That means that the problem has solution, a unique solution at that. All right, and the reason why I want to find this tau function is the so-called Kiev formula. So this has been done in 2013. There is actually a full solution of this tau function. It's one of the most difficult integrable systems, or classically integrable systems ever known, but these people have, they were smart enough to solve it. I'm talking about Camayo. This is from 2003. This is a direct outcome, or direct new result that came from the AGT conjecture. I think that Alba is probably going to tell people more about that. I hope that you're going to listen. It's a beautiful story, actually. But the thing is, and this is the surprise, that this tau function, the thing that I've told you, has nothing to do with conformal field theory. Yeah, I'm talking about flat holomorphic connections. Well, I mean, flat holomorphic connections have some issues with conformal field theory. But the tau function can be basically solved, or can be expressed in terms of conformal blocks. There is a bit of ambiguity there if I mean classical or C equals 1 conformal blocks. For the people in the known, I mean, I'm talking about C equals 1 conformal blocks here. And this expression for B is, I mean, it's basically known since the outset of conformal field theory in the 80s. I guess Zamolodchikov wrote some recursion formulas for this, and the recursion can be solved using Nekrasov functions. This is a way to phrase that. There are some alternative ways which are actually more numerically interesting. I mean, there are advantages numerically, but the important bit for us is that these conformal blocks, they are parameterized in terms of monodromy data. So they have a natural expansion in terms of monodromy data. I can extract monodromy data by finding for eta, which is a bit different there. It's I'm calling eta with a tilde. It's related to the eta that I wrote before, and sigma. And sigma that I write there is exactly the same sigma that I wrote before. It has to do with this compositive monodromy. And well, right. C equals 1.
Sorry, why is C equal to 1? Because
C
typically...
equals 1, yeah, C equals 1 here appears naturally because these people, they solve it by considering these holonomic fields by Jimbo. So there is a bit of history behind it. The usual way you think about that in conformal field theory is using semi-classical blocks, because semi-classical blocks, they have the null vector condition of Liouville or the representation theory of Virasoro. They are naturally translated to Fuchsian differential equations.
But typically in AGT, you have C different from 1.
Yeah, in AGT, you have any C, yeah. This is B equals I in the AGT. Yeah, but they give it because they solved it using this conformal blocks applied to these holonomic fields that Jimbo defined in the 80s.
But for C different from 1, you don't know the conformal blocks.
Well, for C equals 1, there are ways to phrase that in terms of Nekrasov functions. They are different from this. Yeah.
But they are not known. They are known only perturbatively.
Yeah. You only have the perturbation. That's true. But I mean, there are alternative formulas. I mean, this is there's P and 1 over B is inside here. It's just that you don't have this interpretation in terms of accessory parameters of the differential equations anymore. I mean, it's the differential equation that arises from the word identity there, they are different. And in our case, there are some extra structure that shows up because you have C equals 1 or C equals infinity. So the conditions that you want to solve, I mean, those initial conditions that I showed you in the last slide, they are translated into the 0 of this tau function. This was very hard to understand in this language. And that the log derivative of the tau function gives this accessory parameter k. I mean, there's some extra stuff here, but this is basically trivial. And I mean, from the machine point of view, I mean, this is it. I mean, you basically implement that in the computer, and you crank up your lever, and you find monodromy parameters using these two functions. It's just that, of course, things are not so trivial. But I just want to state that this construction generalizes. Any Fuchsian differential, any number of singular points has a associated tau function that can be solved using, well, Nekrasov functions, but this is usually not the easiest way to think about those. And but the accessory parameters of the Fuchsian differential equation can be related to translated, I should say, to monodromy data using this tau function. All right, so now it comes to, I did this slide already by answering your question, but now you can ask, I mean, like he did 15 minutes ago, why do you need to worry about monodromy data? Well, like I told you, right? I mean, usually you solve using Frobenius method, you solve for local solutions, local expansions of solutions. But this is not the problem that we want to solve. I mean, the problem that we want to solve is to write these local solutions as combinations of solutions at different points. Say, the usual scattering problem, you have a particle coming from minus infinity, and you write this particle as a combination of reflected wave and a transmitted wave. I mean, this is the usual problem that you want to solve in physics. Well, in order to do that, you need this so-called connection matrix. So the connection matrix, or the simplified version I'm writing here, basically tells you how to write a set of local solutions that you have at one singular point, zk, to another solution that you have at zl, a different singular point. And this problem is a hard problem. This problem you cannot solve by just monodromy data. But you can constrain this problem well enough. Like to see that it affects the monodromy data, you just write explicit formulas for the monodromy data based on the zk. So for zk, it's just a diagonal form that I showed you. But for ZL, you need to translate the solution that you find at zk to ZL. So suppose that you know the connection matrix, then the function at ZL would be that form, will have that form. Well, I mean, okay, these are 4 unknowns there, but you know that the trace of this composite monodromy data, which I'm called sigma KL, it depends on the entries of C. So it somehow has some partial influence on the values of C, or the entries of C. There are many ways to further constrain C. In our case, our differential equations, they all come with a reality condition. They all come from wave equation in some background, for instance, like in the problem that I want to solve. And for that, you have some conserved currents. The conserved current allows you to choose a natural normalization for these solutions. In general, you don't have those, and this is exactly where this ambiguity comes from. A simpler problem, and the problem that you don't have to worry about this, is the problem where you have the triangular connection. What does that mean? I'm going to show you examples in the next slide, but it means basically that one of the solutions is just related to the other one. I mean, a solution that has a definite behavior at one singular point can be written as some constant times a solution that has a definite behavior at another singular point. These connections, the triangular connections, they are very important for the problem of quasi-normal modes and the eigenvalue that I'm going to show in the next slide. But they can be solved easily using this, because assuming that CK is triangular is equivalent to assuming, for instance, that this composite monodromy parameter is just the sum of the single monodromy parameters here. I'm not sure if this is correct. I have to enlarge this a little bit. There are alternative ways to solving that, and this is more complicated by just parameterizing in terms of Hentschel-Nielsen coordinates, but this is more amenable. I mean, it's easier to deal with, especially if you were working into confluent limits, like some of the black holes that we encounter. Okay. Right, and I guess that this was similar to the point I just gave you, so I'm going to be brief here. There is the tau function implements this Riemann-Hilbert map between the parameters in the differential equation, which are parameterized by T and K there, and the monodromy data. And the map is actually canonical in the classical mechanics point of perspective. So there is a natural Poisson bracketing of these accessory parameters of the differential equation, and the canonical Poisson bracket is translated into this Goldman or Thibault Poisson bracket of monodromy parameters. Well, semi-classically, and this is probably something you're going to hear after lunch, this is known by this level 2 null vector condition of Liouville field theory. There are a null vector at level 2. Null vector satisfies a conformal word identity that is a Fuchsian equation. And the Fuchsian equation is exactly of the form that we find here if you take B to infinity. There are many ways to compute this level 2 vector condition. This is known since the 80s. You can use this Zamolodchikov recursion formula, which is actually very fast. Numerically, it's very efficient. And people do that nowadays to do conformal bootstrap for any value of B, for any value of the central charge. The one that I just presented to you, these Nekrasov expansions, and they come exactly because of this deep connection between the CFT and n equals 2 partition functions of instantons in super Young Mills, in this case SU2 super Young Mills. These are also valid for any B, I mean the Nekrasov expansion itself. Their relation to the Fuchsian equation is only clear for B equals I, meaning C equals 1 or C equals infinity. And there is an alternative way, which is the most numerically satisfying, and this is something I won't have time to show you. I guess I ran out of time already. Oh no, it's not that bad. It's not that bad, yes. No, sure, great. The RiemannHillbert problem is writes these solutions, this tau function, in terms of projection operators. It's actually a very beautiful construct. It has nothing to do with the IGT or Nekrasov expansion, but it's probably something that has to do with CFT. I would like to actually know how and why. It's better to explain that in the case of 4 singular points. Can I use the board? So this will be quick. If I didn't have time, I wouldn't bother, but. The other way around. Great. No, yeah, I mean, I guess that, yeah, this is enough. Okay, good, thanks. So you have this picture of this singular points of Hoyne equation. So, yeah. And then, I mean, this is the way the solution behaves in complex plane. You have branch cuts everywhere. I'm not going to draw those, but oh, okay. But as I told you, the monodromy properties, they are basically parameterized by these two complex numbers. Okay, just that people can see that, right? Perhaps I can choose the. Yeah, I mean, it's not exactly this one, but this. So I'm trying to say that here you have this two singular points. I'm choosing T naught to be smaller than absolute value smaller than 1. If it's not, then you can use some action in the braid group to translate that. That's a good thing about of the tau functions, that you know how the braid group acts on that. So I'm telling you that this circle here that corresponds to this composite monodromy, they are parameterized by these two complex numbers, or the information I want about this is parameterized by these two complex numbers. Well, these people, I mean, this is the beautiful thing about this. They introduce a Plemelli operator that acts on the space of pairs of complex functions, and they project the complex functions inside the unit disk that have these analytic properties. So they have these monodromy properties here. And this problem you can solve. This problem is solved by hypergeometric functions. Now they introduce another Plemelli operator that takes these functions in the outside, so the principal part of the function, and they project into functions with these analytic properties. So you have the monodromy at 1, monodromy at infinity, and the composite monodromy also parameterized by sigma. Okay, so they construct these two Plemelli operators, and they write the tau function as the determinant of the composition of these two. And this is the tau function, this up to some trivial part here. Well, now you can understand from this, you can understand where it's 0. When it's 0, it means that after you project, there is some kernel. So it means that there is actually a function with those analytic properties. And that's why you get the tau equals 0 as one of the conditions. From this perspective, the accessory parameters, this log derivative is something completely out of question. It's completely hard to understand, but anyway, you have to work on both hands. So this is actually the interpretation of this here. And this cost me a lot to to get. I mean, this, for me, it was, at least it was very hard to understand. Yeah, it just, I guess it's enough. Okay, so where was I? So yeah, the important bit is that because this is a determinant, and this is a Fredholm operator, which is not so, well, clear or crystalline, it means that numerically this is stable. You can write in the computer, you have arbitrary precision, and you can extract numbers with some confidence out of this. Unlike generic trans-series where this sort of thing is very hard to deal with. All right. So, okay, so let me talk about the actual problem. The solution, or the problem that we have at hand of quasi-normal modes of black holes, they all tied in this category for, well, for a large number of black holes, and this is something that is trivial at all, but I'm going to this as a fact. The wave equation for scalar fields, for instance, is separable. So it means that you can write solutions as these solutions for ordinary differential equations. The part that's associated to the Killing vector fields, they are trivial, just exponentials, but you also have non-trivial part. And the non-trivial part, they usually satisfy some Fuchsian differential equations. Well, why is that? Or why there are coordinates for generic black holes in which these associated differential equations are Fuchsian? I wish I knew. I'm sure that there is something underlying, some deep underlying structure there, but this is just how it is. I mean, I think that even these people like Kutros and Plebansky and these people, they don't really know why.
Omega is the rotation frequency of the two black holes.
Yeah, this is just the usual.
No. Sorry. Omega is the quasi-normal mode frequency.
Yeah, it's the frequency.
So, but you have omega L and M. You have omega L and M, which is the meaning of a different.
Right. Omega is just the eigenvalue of time translation. M is the eigenvalue of rotation. I'm thinking about the usual Kerr black hole. L is some parameter that parameterizes this, in this case, the separation constant. So you can think of that as L times L plus 2 in J squared. It's just that it's not L times L plus 2 anymore, or L plus 1, but sorry. L plus 2 is the, yes, I'm thinking about 5 dimensions. Right, so the equation is separable, and the problems that we need to solve are actually the kind of problems that I just presented to you in a mathematical sense. The angular equation, for instance, you want a solution that's both regular at the North Pole and the South Pole. So you want the connection matrix between solutions at the North Pole and the South Pole to be triangular. When you think about the radial equation, at least for the quasi-normal modes problem, it's sort of the same thing. You have usually conditions, well, first of all, there is another piece of non-trivial evidence. If you work in Boyer link with this type of coordinates for the black hole, usually, and this is also something that's a bit puzzling, the positions of the horizons, they are singular points of the differential equation. I don't know why, but they are. So, for instance, for the Kerr black hole, you have singular points at R plus and I minus, the Cauchy and the outer horizon of the black hole. For more generic black holes, you may have positions which are unphysical, say at the complex R, but they all, in this complexified space-time sense, they all have a Killing vector field which becomes null there, in the complex sense point of view. I don't know why, but this is what happens. You also have a singular point at infinity. In the case of Kerr, this is sort of complicated. It's more complicated than it should be, because the equation that you have, the Hoyne equation that you have, is confluent. So you have a more complicated analytic structure in the infinity. Infinity is also a singular point there, and there are problems that arise there from the from the analytic structure. But if you work in ADS5, you also have a singular point at infinity. Well, usually the condition that you have to solve quasi-normal mode problems, they are very similar to the conditions that you have for this angular equation. They have some no flux, or no seeping out flux at the outer horizon at infinity. So whatever comes out of the outer horizon comes back at infinity. So you have some sort of steady wave between those 2 points. And this also translates into a triangular connection matrix. So you see, you don't need to know all the connection matrix. You only need to know that's triangular in order to solve this problem. In order to solve this scattering, you can also sort of trick your way around not knowing the connection matrix in full, but that's because you have a natural way to normalize the solutions at 0 and R plus and infinity. There are some formulas that also in the papers I've written a few years ago. Okay, so all right. So I guess that the whole program, and I think the rest of the talk will just be the results. But before I get there, let me just tell you why you should care about this, right? Well, of course, I mean, everybody has their own preferred method to computing quasi-normal modes. I mean, this is 40-year-old problem in the literature. You can do mathematics if you want to. Just right there, and it knows enough about Hoyne functions that will give you an answer. The black holes that we find here, they certainly fall into those classes. I mean, right after we wrote this problem of ADS5, there were these nice people that came exactly with this program. I mean, why are we worrying about all this monodromy? Because I can do that using mathematical implementation of Hoyne function. That's great. The tau function, the solution, the method that I've just presented to you, it gives some sort of formal solution. So you get this tau equals 0 and the log derivative of tau being the accessory parameter k. However, first of all, you don't have any numerical issues that usually come with the integration of the equation itself, especially if you work near the extremal limit. In the extremal limit, the solutions, they tend to oscillate very fast near the outer horizon, and it's very hard to filter for overtones using the usual methods. In this case, this way I'm writing here, this doesn't happen. Simply doesn't happen. There is no way around that. Okay.
There is a question.
What do you have in mind when you say analytical method exists for a number of black holes?
Well, I guess that, I mean, there are various approximation schemes, right, when you do WKB or things of the sort.
But typically and numerically, not...
No, I mean, I'm calling it analytical. Numerically, you can solve numerically the Hoyne function. Right, I guess that's clear. But also analytic, you do WKB approximations and things like that.
I'm talking,
sort of. It's physicist jargon. Okay, so the point here is that the tau function has this 20 years or 30 years of work into it. For instance, you know that the tau function is actually metamorphic in the complex plane, and the zeros of the tau function are all isolated. Sometimes they do, well, they cluster, they get together, but in principle they are isolated. So, I mean, methods to find roots, so numerical methods to find roots, they usually they work very well. There is an extra thing, and this is about structure, right? There is this relation to conformal blocks, which is basically explicit. I mean, it's there, and I have this underlying feeling that if you want to understand what conformal field theory has to do with black holes, this is the proper way to think about that. I know there are many people that say many different things. This is not the same conformal symmetry that these people from Harvard they were doing a few years back. It is completely different, and it's based on chiral symmetry. And there is some twistorial favor to it because it's you act on theta and r separately. I'm not proposing I know everything what's going on, but I'm sure that this has nothing to do with the way they presented it. I wish I knew, but anyway, resurgent here is clear. I mean, this is one of the nice things about the Penlev S6 tau function. I told you before, you have a way to know how the action of the braid group is implemented in the plane level S6. You also have alternative ways to think about these researches for plane level F5 and 3, which are the ones that show up here. And for plane level S6 in particular, this allows for the choice of expansion point. You don't need to expand around t equals 0. And I gave you the expansion around t equals 0. You can use this action of the braid group to implement the expansion around t equals 1 or t equals infinity. And this is, again, from the numerical point of view, this is exactly the same that you have for hypergeometric. For hypergeometric function, you have the expansion about 0, about 1, and about infinity, and you have a way to connect these 3 expansions. This is the important bit. This is why you put it in the computer, gives you a number, whatever you have. You do have the same thing for plane level S6. It is the same thing. I mean, you can, in principle, write the expansion around each of the points, and you have a way to connect these expansions. And this goes into this last point. There are numerically stable methods in the sense that you can move around the point in the complex plane in the dependence on of the value that you get. But numerically, they exist. I mean, this Fredholm determinant works for it. And perhaps more important for the people that actually work on applications, you don't need to fall into Hoyne class anymore. You can have a generic Fuchsian equation. This still works. All right. So about the results, I guess I have 10 minutes. Good. Right. That will be fast. You can work with scalar KNMs. Okay. Okay. There will be lunch after that, so everybody will be hungry. Okay. Right. The 5-dimensional Kerr ADS black hole is sort of a perfect test bed for this, because the equation that you have is purely Hoyne equation, and the parameters that you get there are easily readable. For the angular part, you see that the theta parameters, which correspond to the single monodromies, they are, well, they have very easy interpretation. It's basically the delta there is the conformal weight, the conformal dimension. M1 and M2 are the eigenvalues of the 2 angular momentum that you have in 5 dimensions, of the 2 Weyl subgroup of the rotation group. And the analog of the expansion parameter is given by this ratio of the difference between the 2 rotation parameters, A1 and A2. Well, you can, the accessory parameter is given by that horrible expansion, but you can use that using any computer algebra system and the Nekrasov expansion to give an expansion for the angular eigenvalue by just implementing this condition for triangular connection matrix. So I guess this is well enough. You can do the same thing for single rotating close to 1. This is something we're working now because there are some physical interesting things happening there. Well, this gives us some procedural way to work this. People in the literature, they have been not able to go over 2nd order or 3rd order, I think. Right, and that's that. The radial equation is also Hoyne, pure Hoyne, no confluence. The theta parameters, they have this nice, strange interpretation, which is also something I wish I knew more about. There's probably something deeper into that, because the term that I writing here between brackets is basically the entropy income or the entropy variation of the black hole as it absorbs a quanta of energy omega, angular momenta M1 and M2. You see the dependence on the temperature here makes the okay.
The expansion parameter is A2 minus A1?
Yeah, in the angular case.
You mean that for A2 equal to 1, you know the exact solution?
You know the exact solution. This is not
for any omega.
For any omega, yes. Mm-hmm. When A2 is equal to A1, you fall into a hypergeometric equation. It's not Hoyne anymore.
This is the extremal case, A2 equal to 1?
Sorry? No, it's not extremal. It's equally rotating. So the temperature is not 0. You have 2 separate horizons, but the 2 angular momenta around theta 1 and theta 2 are the same. Right. So you have that for the radio equation, you have the accessory parameter, and you have a way to solve analytically. I mean, you give some asymptotic expansions. This is basically, I mean, there is nothing really remarkable about this. It's just that you know exactly what the structure of the trans series that you get. You know that the trans series is a trans series on R plus, the outer horizon, and log of R plus. And this is the only new thing you understand about the nature of the expansion. I told you that there is a nice way to interpret that in terms of two-dimensional CFT, and this is represented in the upper part. You basically, you have two, let me go back here. Yeah, you have these three positions for the horizon, R plus and R minus and R naught. R naught is one of these cases where I told you, I mean, this is not a horizon in the physical sense, but R naught squared is negative, so this is a purely imaginary number. And because this is a purely imaginary number, the T naught there, which would be the temperature, is imaginary. It doesn't mean anything physically, but it means that the theta is real for those cases. For R plus and R minus, then temperature is real, everything's better, although it's a bit strange to think about the inner horizon to absorb quanta, but anyway, as a separate system from the outer horizon, but thetas are imaginary. And in these cases, I mean, if you work the semi-classical 2D conformal block, then the inner, the outer horizon, they have this. Since they are imaginary, you have a cylinder. The geometry around those points are more like a cylinder than a conical defect. So you have this. If I say word shit, will people throw tomatoes at me? You have this two-dimensional Riemann surface associated to this conformal blocks expansion. And the momenta, the Liouville momenta in this case is just the entropy going around the cylinder. And these singular points, the conical defects, they are related to basically the frequency, at least when R plus is small, and the conformal dimension of the perturbation delta at infinity. When omega is real, this is a unitary description. Well, these are the. Okay, sorry. No, yeah, but people at home.
What are the coordinates of the worldsheet?
It's basically R squared, the radial coordinate squared. It's a complex plane. It's a complex R squared. Yeah, it's a Riemann sphere. It's only dimension one. Okay. All right. So this is it. I mean, you can definitely do it numerically. You find these unstable modes that people they talk about thermodynamically since the 90s. So for some range of radii, and I guess this is A small as well, the rotation parameter is small, you find a very discrete but positive imaginary part for this quasi-normal modes for L equals 1. Also happens for L equals 2. You can do, these are all fundamental modes, but you can do excited modes as well. It's just a bit hard to follow. But you'll see that you also have these unstable modes that show up where the thermodynamical argument says that they should. Anyway, I guess this is illustrative but not very informative, so I can go forward. There are some strange, if you know the usual discussion about ADS5 black holes, people say that there are two types of instabilities. The instabilities that I showed to you, and the so-called Emparan-Myers instability that show up when you have large rotational parameters. We don't find any hints for those here. As you increase the rotational parameter in this, well, this would be the next slide actually. So let me go. As you increase, the modes actually become stable.
Go slowly on this point because it is really a lot of physics in that.
Yeah,
so
sure.
Please.
Right. So as you increase the rotational parameter, in this case A12 is just the difference between the two rotational parameters, the modes, they become less and less unstable until they become stable again at A12 equals to 0.045. When A plus is big enough, they also become stable. And although you have this increasing window of instability. So in this case here, you see that the range, as you increase the value of L, increases. Like 0.3 here, so for L equals 4, the most unstable mode is still unstable. This is just a thermodynamic argument. The thermodynamic argument actually is just that these modes, they are supposed to be unstable, where this quantity here is negative. This is the super radius condition. The omega here for larger L's is larger. So there is a competing effect between M2 becoming, or the angular velocity of the black hole becoming increasing and omega becoming smaller. The real part of omega is what sets here. And usually the real part of omega decreases as you increase the size of the black hole up to a point. Then it begins increasing again. Okay, we have this, I mean, they become less unstable in the sense that the amplitude is smaller as L increases, but the window also enlarges. We actually have no hint that this is going to happen at large values of R+. And this is one of the things that's actually bothering me a bit. Oh, yes?
Thank you. Actually, in the limit where L goes to infinity, you can show that it extends to all parameter space.
All right. So I mean,
you see
you
what
mean that
you are saying
this window here becomes larger and larger without end.
All the way up to the.
Okay. Yeah, I have absolutely no idea how to see this here.
At least, here I'm using the intuition from the equal angular momentum case. Okay.
Sorry, for the equals
from
for?
the equal angular momentum case,
okay.
where A1 is equal to A2. At least in that case, that happens.
Okay. Yeah, I wish. I mean, I don't think I have any way to translate that into this language.
And the angular velocity of the black hole in ADS units, so of the ADS radius, it's always bigger than 1 or equal to 1. So it's rotating with a velocity that is faster than the velocity of light. In the limit where L goes to infinity, it approaches 1. So unstable black holes always have omega times L greater or equal to 1.
Okay. Yeah, I don't think I wrote the actual values for omega here, but you are right in the sense that there is a 1 minus A1 in the denominator. Okay. Right. You can do vector perturbations as well. Vector perturbations are a bit more complicated because it's only been shown, I think in 2013, 2014 perhaps, that the equations are separable. And they are separable by introducing a new parameter. They call it mu. These people, Frolovic, Trosch, they dub the whole thing mu separability. And the physical interpretation of mu is actually something that's very obscure in the language. We had this paper because about this in the beginning of 2020. And you can actually solve the problem by using the isomonodromy method, because the equations that you get at the end of the day, they are not the Hoyne equations. They are the Hoyne equations plus the extra apparent singularity. This is the new thing there. And by the argument that I just gave you, that the physical data should only depend on monodromy data, like the structure of the connection matrix or indeed the scattering coefficients. That means that you can move this around and still have the same physical system if you move it around this isomonodromy line. So you can basically find the isomonodromy line between the two radial and angular systems in order that they allow for solution of the system at least a class of solutions in the system with the same monodromy data. When you do that, the value for mu is actually set, and this is something we have not written down, but it's basically, it's kind of easy to see that the value of mu that's set has to do with the polarization of the modes. We're talking about vector modes here, vector modes in 5 dimensions that have 3 polarizations, and mu sets the relative strength between the 2 magnetic polarizations. And of course, this is set by the geometry of the space-time. Not all modes, not all polarizations will be available. You also have some evidence for superradiance, although we did not go through with that here too well. I guess it's expected also on thermodynamic grounds. That is also okay. You can do also the black hole that people take photographs of. This is work with João Paulo, and we have, I mean, we just repeat the problems that are solved for like 20 years, solving for the angular eigenvalue. You have the usual term for spin S spheroidal harmonics here, but you can get the series rather easily from the monodromy expansion, for the expression of the tau function. And you can solve for the radial equation. I just showed to you here the values for thetas, the single monodromy values, because they are not of the form of I times the absorption of entropy over temperature anymore. You get an extra real term depending on the spin of the field. So this is also to dispel some problems. You have the usual expressions for the temperature and so on. And you can actually take the conformal limit of the monodromy condition that are presented to you. You get this as new monodromy conditions between the monodromy data. Eta, it's very small here, but I hope you can figure, and sigma. And now the tau function that you have is not related to point level S6 anymore, it's related to point level F5. It's a bit of a different beast, because now you have this strange structure at infinity, but you still can work this using the same procedure, actually using these Fredholm determinants. And you can repeat again the modes that people computed. I mean, this is already 40 years old, but it's just to show that you fall onto the expected numerical values. So this is the standard literature, Berti, Cardoso, and Starinets. Yeah, and we repeated that in this paper from last year. And the numerical error, numerical difference between the two is actually quite well controlled. So in this case, you are getting the same 10 decimal places between our result and theirs for the frequency, and the 9 decimal places for the angular eigenvalue. I just showed to you here that, I mean, I told you the continuous fraction method that they use is akin to our own homological recursion that we have in CFT. It's the same one. And both are expected to fail as you come close to the extremal limit. The CFT version of this actually is related to these Whittaker modules of CFT. It's a slightly different beast than the usual Verma modules that you have, but they are equally iteratable.
I can understand if you are approaching the extremal point from non-extremal solutions, that it's a problem. But you can also solve the equations directly at extremality, right? Because now you have a degenerate horizon, so the boundary conditions will have to...
Yes.
And in that case, it should not be problematic at all, right? At least that's my experience. You know?
Yeah, I will beg to slightly differ, because as you come close to this extremal limits, you have 2 types of modes usually. Either they become co-rotating, so the omega becomes close to the angular eigenvalue, or they don't. So this is Aristotelian categorization so far. These co-rotating limits, they show up in these higher rotating limits, except when L equals 5 for some strange reason. I have this figure here. I hope that people can see that at home. This is a nice L equals 3 spheroidal harmonics. And in our case, you can actually do this expansion of these modes, at least the co-rotating modes, near the extremal case. And mu here is like an extremal parameter. And although it's true that the modes, they either go to there or not, you don't know a priori how they go there. When the modes, they become, they are co-rotating, they basically decouple if you just write the equation in the extremal case. When you write the equation in the extremal case, you assume that the t parameter goes to 0 at the same time as theta goes to infinity. But in this case, theta does not go to infinity. So this is not, they are not described by the confluent version of the Tolkowski equation in this case.
So 1 over alpha is the angular velocity in the extremal case, right? So it's when little omega approaches the black hole velocity at extremality. Right, so that 1/2, I'm trying to understand 1/2. The 1/2 is because in the extremal limit, the angular velocity of the black hole that usually we call capital omega is equal to 1/2, right?
Yeah,
in these units.
So.
And what you are saying is that there are modes that approach,
Yeah, so if you look here, I guess you can get the idea. So by just taking the confluence of the differential equation, you assume that theta goes to infinity. But these modes, they omega go to m times big omega as t goes to 0.
Yes.
So this has actually a finite limit.
Yes.
So you don't, they are not described by the confluent version of the Tolkowski equation.
Okay.
In the physicist language, they decouple.
Yes, but you can still solve for it analytically. You can still solve for it at extremality.
Yes, you can solve for it, but you have to know a priori which is which. Which modes decouple and which modes do not.
Actually, it is known that at least in 4 dimensions.
This is 4 dimensions.
4 dimensions with the rotation with charge, that there are 2 families of quasi-normal modes for a given set of quantum numbers, L, M. And the one that approaches omega equals to m times capital omega is what is called typically the near horizon modes. So the imaginary part of the frequency approaches 0 at extremality.
Yes.
And you can even do a near horizon expansion away from extremality to capture. The other ones that do not approach it are what are called the photon sphere modes, because in the limit, in the WKB limit where m goes to infinity, m equals to L goes to infinity, you can see that the imaginary part of the frequency does not go to 0 at extremality. So there are clearly these 2 sets of families, and they have a different behavior.
Yeah, well, I don't know why this is not showing up, but yeah, it's showing up now. This is exactly what we found, by the way. Why? Some delay? Yeah, I think there's some delay.
You're over time. At some point, everything stops working.
No, yeah, I have to finish soon. Sorry about that. Yeah, so this is exactly what we find, that, for instance, there are modes like this one, whose imaginary part do not go to 0, as you have, these are the extremal parameter. When it comes close to 0, you have the extremal point. And these modes, okay. These modes, they are described by the confluent version of the Tolkowski equation. And in our language, they are described by this third Poincaré transcendent. There are modes that do not come to that. I mean, like this one, where the imaginary part goes to 0 as the extremal parameter goes to 0. In this case, you have this sigma parameter, the monodromy parameter being 1 plus imaginary number. You also can have those to be real, like here, and then you have this quadratic behavior. Well, this is actually not 0. Yes, I came back for some reason. Right. And yeah, anyway, this is the real part, so there is a quadratic dependence on the real part of the imaginary number. Anyway, you do have those 2 different types, but we don't know a priori which goes to which behavior. And this was part of our motivation to studying Rice and Nordstrom, because unlike what happens to Kerr, in Rice and Nordstrom, you can control this extra bit here, which is m times omega in the case of Kerr, and m can only be integer. In this case, you can vary Q continuously. And you find actually that there are something very strange happening very close to the extremal point. This is the usual way people parameterize the Q going to infinity in Q go to M in Heisenberg-Nordstrom. So you see that there is some structure there very close to Q over M equals 1, and you can again define this extremality parameter and read what's going on a bit better. And you see that there is actually a very sharp bifurcation point here between one type of behavior and the other. So for this is spin half, the blue part is spin 0, and you show that if Q is larger than a critical value, so this is 0.1, then the imaginary part goes to 0 in the extremal point, the extremal limit, above this value, so if Q is larger than this, and it goes abruptly to a value which is not 0 for Q is smaller than point, and it's a slightly larger value for spinorial, I shouldn't say perturbations, but spinorial fields. Okay, so actually this gives, this was something that's rather complicated in literature before. You find that these modes, they do not show, I mean, they correspond to some particular values for L, they do not show in the extremal version of the Tolkowski equation. And this is in contradiction with some works that people have done before, this group like Casals, and I'm finishing. So I don't have time to talk about this. I'll be happy to, more than happy. It's just some, you can think of this as a generalization of what we've done. Mathematically speaking, there is no way, there is nothing that prevents us to construct the same thing for a larger number of points. And this has this application in conformal maps. So let me just jump to the conclusion. What I hope we learned. Well, I hope that I convince you that what I have is not only a formal solution. I mean, in the sense that, okay, I give you these conditions, and these conditions tell me that a hard problem is equivalent to an equally hard problem. I'm telling you that this new piece of information is actually amenable. I can work with that, either numerically or analytically. I think, and this is, I mean, this can come because I have my own idiosyncrasies to think about this, having thought about this problem for such a long time. But I do think that thinking about monodromy is a better way to think about these problems in the generically, even when you use these usual methods, because you can read the monodromy properties from continuous fractions and from Hughes determinant the usual numerical way to deal with the connection problems in Hoyne equation. Well. Good question, and one I wish to look better at it, is any separable black hole leads to a Fuchsian or a confluent limit of a Fuchsian differential equation. I wish I knew. I wish there was something more understood about this. But I'm telling you that if it does, then I can treat that using this method. Well, the factorization of the space-time conformal blocks into this, it is something that you can see from ADS5. I did not have time to do that. But you can think about perturbations in ADS5 as four-dimensional versions of conformal blocks. It's just classical conformal blocks in 4 dimensions. And the whole program, I mean, in principle, the philosophy of the whole program is that you can factorize those 4-dimensional conformal blocks into 2-dimensional conformal blocks. They are chiral ones, but you can do that. Is there anything else there? I don't know. Well, and I also would like to show you that in general, you do have to think about all these monodromy coordinates. I mean, dealing with one of those allows you to solve particular problems, but usually when you have, or you are coming close to limits, then it becomes very difficult to understand them separately. So I guess this is it. Thank you very much for listening to me.
Let's thank the speaker. We only have time for questions from remote. Is there anybody from remote? There are no remote questions. Then we can allow the organizer.
You can get into Zoom. And,
it's the only we only get one question.
It's a quick one. So maybe I didn't understand. Did you mention that you do not recover the Emparan-Myers instability?
Yeah, I have not found it.
But why? I mean, is there?
I think
this is for discussion.
Because you are in 5 dimensions. If you were in 7 dimensions, I think 7 or 9, but 7 I think you would find. The point is that this ultra spinning instability in ADS backgrounds, already in asymptotic flat case, it only appears above a certain dimension.
But I thought it happened at 5, but...
No, in five there isn't. And there is a criteria for it, actually, a thermodynamic criteria for it that is based on the Hessian of the system. And that gives you the boundary above which the instability can appear.
Yeah, that's usually the problem I have with this sort of thermodynamic arguments. Because nobody tells you that there is no super selection rule or selection rule preventing you from getting those transitions. So I would like to see those. But I have to say, anticipating results that will come out soon, we did show an instability for higher spin black holes. I'm not sure it's the. I'm pretty confident that actually it's not the Emperor-Myers, because the Emperor-Myers should show at large black holes as well.
Okay, let's thank everybody, and especially the speaker once again.